In this video, we're going to talk about properties of inverses. So you do want to watch the inverse, how to find an inverse first, and then watch this video. So the domain for the inverse function is the range of f of x. We talked about that pretty extensively in the last video. We're swapping the domain and the range. That's how the inverse works. But the thing we haven't talked about and is important is that in order for a function to have an inverse, it must be 1-to-1. So let's recall what 1-to-1 is. 1-to-1, you might remember, it passes the horizontal line test. The horizontal line test. So that's from a while ago. Passes the horizontal line test. And I'm giving an example that doesn't pass the horizontal line test. X squared, right? X squared does not pass the horizontal line test. So if I draw this 0, 0, here, let me do my check marks in blue. 1, 2, 3, 4, 1, 2. Okay. So it goes 1, 1, and 2, 4 on both sides. Okay. That does not pass the horizontal line test. We know this. If I draw a line, boop, hits twice. So I need to restrict this equation so that I could find the inverse of it. So I'm going to restrict it to being just half of the graph. So I'm going to take the positive half. I'm going to go ahead and erase a little bit of what I have here. I'm going to take that side of the graph. So I'm going to restrict the domain to being from 0 to infinity. That's my restriction. Now it's going to pass the horizontal line test. You could have restricted it to the negative half, but most of the time it just is nicer to work with positives. But now that I've got that, I'm going to find the inverse of the equation. So here we go. F of x equals x squared. So first thing I'm going to do is I'm going to make it a y. Then I'm going to switch x and y. And now I'm going to solve for y. So to solve, I'm going to take the square root of both sides. So y equals the square root of x. And then I'm going to write my final answer with f inverse. And here I'm going to actually write it so that it's on the left side. So there's the inverse. It's the square root of x. But that's based on this restricted x squared. That only works when the domain is restricted to 0 and infinity. It actually does kind of make sense. All right. In fact, I do kind of explore this a little bit down here. If this is, oh, they used h for some reason. Okay, so this is x squared. And this is the square root of x. That's the graph of both of those. You see how there's this kind of cool symmetry across the diagonal y equals x? That's not a coincidence. That kind of symmetry happens with inverses. They have this symmetry across the diagonal. So I want to point out really domain for this square root function is 0 to infinity, right? And its range is also 0 to infinity, the exact opposite of how we've restricted our x squared graph. Okay, now let's look at an example where we're given the graph and we want to find the inverse graphically. So we know that the inverse is literally swapping the domain and range. So here, what I'm going to do is I'm going to pull out some points that are useful to me, like 1, 0, 2, 1. It's another one. Those are like the most useful because at 3, it's a fraction. And I don't see any other nice points. Okay, so I'm going to use that to help me. So the inverse is going to be the exact opposite. Instead of being 1, 0, it's going to be 0, 1. Instead of being 2, 1, it's going to be 1, 2. And visually, I want to kind of replicate this as being symmetrical or reflecting across the diagonal y equals x. That's how the inverse is going to look. It's going to take all the ordered pairs, swap the outputs and inputs, and there you go. That's how the graph looks. It's kind of cool when you see it that way. And it's not by chance. The reason that it ends up reflecting over x is the composition of any of these inverse functions ends up being x. So if I take f of x and I compose it with f inverse, so let me use the composition notation, f composed inverse of x, or I'm taking the inverse and plugging it in, it always comes out to x. The reverse is true. If I take f inverse and compose it with f, in other words, I'm plugging in f, it still comes out to x. So this x is actually relating to the graphical reflection that happens across y equals x. Pretty cool.